Right. So as Max said, we'll now move scale from the whole estate down to phenotyping at the individual tree level. And so really the concept remains the same. We're trying to understand these drivers of growth, G by E by S, but we take another approach and work at the individual tree level. So the basis of our approach is to take LiDAR, as you see there at the top left, point cloud. You saw that in Robin's talk. We have methods to identify and delineate the individual tree crowns within that LiDAR. So that's the image in the bottom left there. And then we can analyse each of those tree crowns in terms of being a three-dimensional shape and generate a large number of metrics characterising each tree crown. So we typically generate of the order of 50 metrics. And we've found, this was early work in the program, we found strong correlations between some of these metrics and the key measures of tree size, so height, diameter, and total stem volume. So really, these methods sort of form the basis of our individual tree phenotyping work. But in more recent work, we also looked deeper into the LiDAR. So we're all aware that we can get a very good DTM out of LiDAR, but it was very interesting to look at that DTM in terms of it being an environmental, a way of characterising environmental effects on tree growth. So we took DTMs and generated a large number of terrain metrics. Some of the simple ones that are easy to understand, things like slope, aspect, but then there's potential to derive quite a large number of metrics, in fact, typically characterising things like soil moisture, solar radiation, and so on. Then we also sort of took stock of the fact that by identifying individual trees, we have their locations and we have measures of their size. And this is the perfect basis to derive what are called competition metrics. So these are widely used in tree growth modelling traditionally. But the restriction in the past was it was difficult to obtain that information, even for model development and particularly for model use. So they haven't been widely used, but this individual tree level analysis of LiDAR really places us well to compute those metrics. And so we're able to characterise the growing environment then of individual trees by looking at what I call site effects or microsite effects by looking at the terrain model and competition effects. And so these graphs underneath illustrate a couple of our phenotypes, tree height and total stem volume. And the green bars illustrate the reduction in error that we achieved from the three best terrain metrics, and the red bars illustrate the reduction in error we achieved using the three best competition metrics. And this was in work in a genetics trial where reducing the error translated into big improvements in heritability estimates. So tree breeders are very interested in that ability, but it also has broader application. I think it's going to improve tree selection and breeding and the information they get out of breeding trials, but it's also going to have other uses. So in the next phase of work, we turned around and rather than applying these methods to a research trial, we applied them to an operational stand. So these images here represent you can't really see them, but effectively every individual tree has been detected, a polygon drawn around its crown, and that range of colour is effectively a colour coding of each tree crown, where red represents high values, blue represents low values. And the image on the top left is our phenotypic data, so by segmenting individual trees, we can estimate their individual heights from the LiDAR. We had a project where the aim was to select trees that were performing exceptionally in the stand, with the idea of going back to the appearance, as an exercise. So the objective was to find superior trees, but we realised pretty quickly if we just go and pick the tallest tree, it could be tall because it's growing on a favourable microsite, or it might be experiencing low competition. So by applying the methods we had developed earlier, we were able to extract the microsite and competition effects within that phenotypic data. So that's illustrated in the top right and bottom left images there. And then thereby isolating more clearly just the genetic component of that phenotypic information. And so, particularly with the microsite image there, You can see there are patches within the stand that they were related when we were out in the field. We could see there were things like northern aspects where trees were growing better. And then there was a series of gullies, shallow gullies and ridges across the stand where height was, clearly changing in response to those effects, as well as effects from competition. So, yeah, this was a really useful methodology to be able to extract this G by E by S, the components of that from the observed phenotypic data. So in the next phase, the idea was then to characterise each tree in terms of its genetic potential and then rank them on that performance value. So this trial was of the order of 35 hectares. We'd identified a total of just over 10,000 trees there, and we ranked them all in terms of their genetic performance by isolating, removing the effects of competition and microsite, and then picked 170 of the best performing trees. So those trees were dotted all over the stand, and we generated a map where, just to have a relatively efficient traverse from tree to tree, because they were pretty randomly spaced around the stand. And then each tree was visited and DNA was sampled from them. And so just very briefly, talking about the work that Natalie Graham carried out, the DNA was then carried through pretty advanced methodology that I don't understand to determine the appearance of those trees. And so the results of that are illustrated in this blue bar graph, where there were a number of parents, and the bars are illustrating the frequency that they appeared in our sample. Now, at face value, you might say, okay, there's clearly one or two parents that are occurring with a much greater frequency there, but it's not, unfortunately, it's not quite that simple. The original seed lot itself had a varying mixture of different parents. So some parents were highly represented in the original seed lot, and others occurred much less frequently. So we can't just take those observations directly. The little graph at the bottom sort of illustrates the approach that was used. So on the x-axis is the frequency of the parent in the original seed lot, and on the y-axis is the frequency of the appearance of that parent in our sample. So quite a few of those parents fall on this sort of one-to-one line, where they're showing up about at the level you'd expect by chance, but the interesting ones deviate from that. And so if we focus on the one circled at the top left there, this is a parent that's appearing much more frequently in our sample of high-performing trees than we would expect relative to its occurrence in the original seed lot. So in other words, this is a parent whose progeny are performing remarkably well in that stand. And so this was a very useful sort of demonstration of the technique. Now to change gear a bit, so as Robin alluded to, we don't just work on LiDAR captured from above. So everything I've spoken about up till now was LiDAR captured from manned aircraft, actually. But here on the top left is illustrated a point cloud we've captured from a UAV, so extremely high density. I think that point cloud's 1,500 points per square metre. We think 15 points per square metre is pretty good, but this is the sort of density we can get from a UAV. But even so, the coverage in the stem zone, I call it, is much less. The great majority of the points lie on the crown. And so, as Robin already mentioned, we also use handheld LiDAR to go in under the canopy and capture point clouds there, where we get very, very dense information characterising the stem and lower branching in particular. So that image bottom left illustrates the type of data you get there. And just with some prototype methods that we're starting to develop, to detect and characterise trees from these extremely dense point clouds, we worked in a trial. It's the Glengarry trial, actually, that John Moore spoke about this morning on his big table of what was measured where. This was the one that had the UAV and terrestrial LiDAR component, as well as all the other measures. Yeah, and we were able, across a set of 600 trees, to demonstrate 97% accuracy in detecting trees. And then by a method of fitting circles to the stem and tracking the stem, we're able to estimate DBH with an R² of almost 0.9. But yeah, as you saw in John's talk, we're also sort of trying to push that a bit further and generate metrics also describing characteristics such as sweep, lean, taper, and yeah, my branchiness measure. And John, usefully covered some of the detail on that. I would really just summarise to say that in that trial, which represented genetic and silvicultural treatments, we observed responses from these, the correlations between these metrics and the ground measures and the sorts of things we'd expect all made sense. So really heartened that these are going to be very useful measurement techniques. And final slide for me, just sort of pulling all that together, that really if we look back and think that by flying above, we can characterise crowns, describe height really well, we can estimate DBH quite well, TSV, but by going under the canopy and capturing detailed information there, we can characterise sweep, lean, taper and so on. But also to mention the disc bot. This is a pretty complex device that's been developed over many years at Scion that allows us to take discs from trees, put them through the disc bot and obtain very detailed information about the variation of key wood properties within those discs. And so in the context of talking about phenotyping, I call this a method to phenotype wood, but really it's a way of looking inside the tree and seeing what's going on. And if we collect discs at multiple heights, we can build quite a detailed map of the three-dimensional variation of wood properties within a tree. And so when we look across all these methodologies, that's quite a useful suite of tools to phenotype crown, stem, and even within tree, and really start to help us understand all these linkages between these different parts of the tree.